I was going to touch on one on the speed of light, which I thought
Yes.
was important, and I was going to ask you a question. So, a bit of a question and answer back and forth on this one. When we look at the sun today, do we see the sun how it was 8 minutes ago, or is that just something science tries to use to prove?
No, it's something we were seeing 8 minutes ago, kind of thing.
Okay.
Because it takes that long for light to travel here.
Okay, so how about the light from the nearest star? Is it Alpha Centauri? It takes about 4 years, right?
Yeah, a little over.
Okay.
But see, that's not the issue.
Okay.
The issue is that a light year is not a time. A light year is only a distance.
Yes.
And it's the distance that the speed of light covers at the current speed of light as measured today on the Earth. However, we've never been outside the solar system to measure the speed of light. We have measured it accurately since 1676. We know physically it's slowing down, and it ought to. Think with me. The second law of thermodynamics, the law of universal decay, applies to all physical entities,
light,
right?
Yes.
So therefore, why would light be the only physical entity that was not affected by the second law? You see, it's illogical.
That's what.
And so, since the second law does affect light, light should be slowing down. Now the question is how much, when, and so forth. But we weren't there. We've never been outside the solar system, so people have to remember, a light year is not a time. I know it has the word year in it, but it's not a time. It's the one hurdle you got to get over. A light year is a distance, roughly 5.8 trillion miles at the current speed of light today.
Yes.
But light, in spite of what we were all taught, and I was too, light is not a true constant. Now, G, gravity, is a true constant. Alpha, the fine particle constant, is a constant. But the speed of light that was taught to us, 186,000 miles a second, 330,000 kilometers per second,
yes.
it is not a constant. And I can prove it. First of all, we have physically seen the speed of light since 1676, roughly 350 years. We have literally physically measured it slowing down since Romer's first measurements.
Okay, but was this measured slowing down in a vacuum? Because I think that scientists do agree that the speed of light is not a constant, but speed of light.
You're talking about it. You're talking about it being slower, say, in water than it is in air, than it is in a vacuum. But remember, Romer's experiments were basically in a vacuum.
Okay.
You don't know how he did it, do you?
No, I've not really looked at it. I've never done it myself.
It was, for 1676, this is pretty clever. Okay.
Yeah, definitely.
By that time, 1676, right? Galileo, the telescope, in the years of 1610, 1620, right?
Yeah.
So he had already found some of the moons of Jupiter, right?
Yes.
The Galilean moons had already been discovered back in the time of Galileo, around 1610, 1620. Now, if you want to measure how far something is away from you, you want to use a triangle, right? Or a straight line measurement if your tape can measure the straight line, but otherwise you can use a triangle. Is that right? So what he did was he did a very clever experiment. Now, of course, the timing has become more accurate since he did it. It's been refined, but what he did was he looked at the eclipse of a moon behind Jupiter. So here's the Earth at a spot, and you witness the moon go behind the planet. And then the Earth moves over here, and you see the moon come out of eclipse here. And that gives you your triangle.
Very good.
And simply by distance, distance out, sorry, you've got an isosceles triangle here, and you measure the time of the eclipse and back, and he had a very good number on the speed of light. Now, was it as accurate as today? No. Were the error bars higher? Yes, no question about that. I'm not talking about that. But he had a really good number, and that's 100 years before the American Revolution.
That's amazing.
Now we have measured it physically since then too, and you can see it. Now remember, you cannot use speed of light measurements that use an atomic clock.
No, no.
You can't throw those all out. It has to be a physical measurement.
Yes, so because all the radiometric datings are not very accurate.
Well, but they're also based on the speed of light. And if the speed of light is slowing down, then the decay slows down and they will match each other. And therefore, you will not see a decay in the speed of light. So you cannot use an atomic clock. You have to use a mechanical, electrical, etc. mechanism and actually physically measure it. You can't use an atomic clock. Throw all those out. Those are just lying to you, in essence, when they talk about measuring the speed of light.
Mm-hmm.
Now, in addition to that, of course, Einstein said you can only measure light going in one direction. Einstein's a pretty interesting guy. So if you think about it, it is possible, I didn't say it was, but it's possible that the speed of light leaving us might be infinite. That we're only measuring it coming back at 186,000 miles a second. You've got other things. The redshift we mentioned in private conversations over. But here's the deal. We have manipulated the speed of light in vacuums in labs.
Yes.
We have actually speeded it up. We have slowed it down. And I'm talking now, I'm a creation scientist. I'm a biblical scientific creationist. You'll say, well, you can't trust me. I'm just saying what I want. No. But these are experiments done by evolutionists. These are evolutionary astronomers, astrophysicists, physicists, who in labs and twice have said that they stopped it and started it again. Now, I disagree with the word. I don't think it's right. I know what they're describing, but I don't think it's the right word. But they can slow it down in a lab. You can speed it up. They say twice they stopped it. Now, to me, that's irrelevant because whether they stopped it or not, if you can manipulate light speed in a laboratory, it is not a constant, period. This isn't just a difference in the speed of light through water, or this is speed of light through a cloud or something of various kinds of atoms. This is a manipulation of the light speed. Therefore, if you can manipulate it, it's not a true constant. Now, again, we've never measured the speed of light outside of our solar system. So how do we know what it is? There is absolutely no experiment that can be devised to measure the speed of light remotely someplace out there. You know, and if you think about the Pioneer anomaly, that may be an indication that the speed of light is not constant, even within the scope of our solar system.
Wait, but when you say our solar system, you're talking about our galaxy, right?
I am not talking about the planets. That is not the solar system. The planets and the sun occupy the solar system.
Yes.
But we have a satellite that just now, launched back in the 70s, just now got to where the sun's magnetic field is no longer the predominant effect.
Wow.
Okay. You see, the solar system and it is not defined by the planets inside. The solar system is really defined by the effect not of the magnetism, but of the gravity of the sun's effect. Now, the sun has 98% of the mass of the entire solar system, and its gravitational field extends way beyond the planets. I mean, way out there. And that's what really defines the solar system. It is not the planets. And so, again, we have one satellite, bless its heart, has a plutonium heart. That's why we still get the signal from it. Well, at least the last time it transmitted. And in this Pioneer anomaly, it shouldn't be exactly where it is based on the laws of physics and the speed of light, etc. So maybe that is actually a proof that the speed of light isn't a true constant either.
Wow.
Because Einstein said, that light could be bent by heavy objects. Now, when he used heavy objects, the term meant stars or galaxies.
Yes, yes.
And we know with absolute certainty that gravity bends light. There is no question about it whatsoever. We have thousands of photographs from Hubble to prove it. We even use it as a research tool in science today. It's called gravitational lensing. It allows us to see galaxies behind galaxies we can't see through. We've proved it. It absolutely happens. So light from this galaxy is emitted outward in all directions. Here's a galaxy, and we're over here, so we can't see through this galaxy. We can't penetrate through it, but we can see this galaxy directly behind it because the light spreads out. But the gravity of this galaxy bends it back in and focuses it at the Earth, where we can see it. So we can see this galaxy that, and to quote you earlier, is invisible to us, but we can see it. We can see it because of this gravitational lensing effect, correct?
Yes.
Now, first of all, that proves that the universe is young and not as old as evolutionists claim. Because you see, this ability to focus where we can see it proves it's young, because if it was old, the light would be diffused and we couldn't see it. So that's a side issue. Now, since we know that light is bent by gravity, right? Again, why is the pioneer anomaly happening? Well, the effect of the sun's gravity is very minimal as far out as it is. I mean, it holds Pluto in place, but this satellite's way beyond that. And so it's at the edge of the gravitational field of the sun. Right now, it's starting to enter into the galactic forces, and it isn't exactly where it ought to be according to math, if the speed of light were constant. And so it may be because of the lowering of the gravitational field out there that the speed of light is different. Now, if we take again a look at Einstein's comments about gravity and light, that light could be bent, right? Well, that means that light can be slowed down, or it redshifted due to gravitational fields that have nothing to do with acceleration or deceleration, because we're simply stretching out the wavelength. That's another thing. We have the second law of thermodynamics. There's lots of things going on here. But we do know that light changes speed based on the medium that it goes through. Now, you mentioned the speed of light in water is slower than the speed of light in air, slower than the speed of light in a vacuum, right?
Yes.
Now, there is no place in the entire universe that gravity does not exist. It is the universal force in nature.
So the gravity of, say, Saturn's moon would be the same as the gravity on Earth right now, or does it have more?
No.
Gravity?
No. Remember, the force of gravity is based on mass and distance. It's an inverse square law. Okay.
Yes.
Now, think with me for a second.
So if there's more mass,
because gravity is constant as a law, as a calculation, the closer to an object, the greater the force, the farther away, the less the force, and so forth, correct? Now, there's no place in the universe that gravity does not exist. It is the single universal force. But when you're between two galaxies, the force of gravity is very thin, very little, very, very low. It's called microgravity, correct? So when we put geosynchronous satellites up and so forth, we're balancing one force with the other to give weightlessness, but the gravity's still there. Now think with me. Close to the Earth, close to the sun, close to the solar system, close to the galaxy, we got a lot of gravity. But in between galaxies, well, gravity is very, very thin. I'm just going to say that in the terms of a medium like water, air. Okay. So think with me. If the speed of light is dependent upon the medium through which it passes, and we know that gravity affects light, then between galaxies, light could travel at very high speeds. But as it enters into a galaxy, it would slow down because of the increase in the gravitational strength. When it enters into a solar system, it would slow down more. When it gets to the Earth, and its gravity being right next to it, would slow down even more. So that again, light could travel either infinite speed or near infinite speed between galaxies, because it's not being slowed down by much.
Like gravitation.
It only slow down when it gets close to them and inside of them. How are we doing?